So now that we've seen the ratio test again, I just want to remind you the main reason that we're interested in infinite series is because we want to create functions, and then we want to say that these functions are different representations of certain other functions. Okay, and so we're going to have these things called power series. And these power series are infinite series of power functions. So I'm going to create a function f of x, which looks like a sum, let's say n equals 0 to infinity, of x to the n, for instance. Okay, and then I want to ask the question, for what values what is the domain of this function? Meaning, for what values does that sum converge, right? Does this rule make sense? And for what values does this rule not make sense? Okay. And notice, the general time when we use a ratio test will be when we have things like x to the power of n, or some particular number to the power of n, or n factorials. Okay. So since we do have something like a number to the power of n, we will use the ratio test. And as I mentioned before, this is going to allow me to say something like, well, for almost all values except for maybe 2, I can tell you whether or not this thing converges or diverges. Okay. So the ratio test would say the terms look like x to the n. So the ratio test asks me to look at a to the n plus 1 over a to the n. Okay, this time it's simple enough, I'm just going to write it. So this would be like an x to the n plus 1 over x to the n. Okay, right? Consecutive terms would look like x to the n plus 1 over x to the n. Okay. I can simplify that as those will cancel out with all of those and leave 1. So I have an absolute value of x. Okay. There's no n's left over, so the limit of consecutive terms is absolute value of x. So, when the absolute value of x is less than 1, my function converges. Okay. When the absolute value of x is greater than 1, my function diverges. And when the absolute value of x is equal to 1, ratio test is inconclusive. Okay. So, when it comes to the domain of this function, what numbers can I plug into my function and have this rule make sense? Where does it, in this case, converge? The answer is when the absolute value of x is less than 1, or at the very least, right, I could say when x is between 1 and negative 1. Okay. Now, when I have it in this form, right, by the way, that's where it's going to converge. That's part of the domain. And I know when it's greater than 1, it absolutely is not. And so then the only remaining question I have is what happens when x is equal to 1 and what happens when x is equal to negative 1? Okay, right? What happens when the absolute value of x is equal to 1, right? Which is when x is 1 and when x is negative 1. And those are the things where I'm going to plug those numbers back into my equation, my formula, my function, and try to figure out does it converge or diverge. And that's the thing that I'm going to do to find the other functions. Okay? All right. So, by the way, when I have something of this form and I can say for all of these values that my function converges, okay, there's a term that's called radius of convergence. Right. And radius of convergence is basically telling me how wide of a net can I cast and still have this thing converge. Okay. So for instance, in this case, the radius of convergence is, that's this number right here, 1, right? Which means that I have this function that more or less is centered around 0. Okay. And I can move 1 unit to the right to 1, 1 unit to the left, negative 1, and everything between negative 1 and 1 is part of the domain of the function. Okay. And then I just have to figure out what's happening at that negative 1 and 1. So as far as a function goes, this function, right, has as its domain, at the very least, all the numbers between negative 1 and 1. And then I still have to figure out what's happening at 1 and -1. Okay. And on Monday of next week, we'll talk about that in more detail, right? We'll go back and we'll talk about some more tests. Okay. But it's very easy to see in this case, if I plug in 1, I have this sum n equals 0 to infinity of 1 to the n, which is just like adding a bunch of 1's together, infinitely many 1's together, so it diverges. Okay. And then also, if I put a negative value in there, -1 in there, right, then I'm summing up a bunch of negative 1's to the n, which is like a 1 minus 1 plus 1 minus 1 plus 1. That diverges also by the test for divergence. It's not getting, those terms are not getting close to 0. Okay, so it turns out this is the final answer. What's the domain of this function up here? That one right there. Okay, and then we've seen from geometric series that we actually know that this thing will sum to, right? Not only do I know which values I can plug in, I understand that it will sum to 1 over 1 minus x. Okay. So this is a function that looks like 1 over 1 minus x. Of course, when we're writing it in this form, it's not so obvious. But in hindsight, I understand because it is a geometric series, it will sum to that. All right. So let's take another one. Let's take another example. Okay, here's one. Okay. So this time, might as well get rid of this. Okay. I'm going to define a function, and it will look like the sum n equals 0 to infinity, and it will look like x to the n over 3 to the n. Right. Let's say I'm interested in that, or if I wanted to write it how I sometimes write it, right? 1 over 3 to the n times x to the n. Okay. So those numbers in front of those x to the n's are like a 1 over 3 to the n. Okay. So this would be a function that would look like a 1 plus a 1/3 x plus a 1/9 x squared plus a 1/27 x cubed plus da 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 da. Right. And so I want to know which values can I plug in for x and have that thing converge. Okay. What's the domain of that function? Okay. And again, what I'm going to do is I'm going to use the ratio test. And that will give me what I'll now call a radius of convergence. It'll tell me what values I could plug into that function generally, and I know what works and what won't work. Okay. So again, my terms look like x to the n over 3 to the n. Okay. Or maybe I could write it as x over 3 to the power of n if I wanted. But let me just say I want a to the n plus 1 over a to the n. X to the n plus 1 over 3 to the n plus 1, and then I'm going to take the reciprocal of this, 3 to the n over x to the n, and I'm going to simplify it. Okay. And when I do that, those will cancel out with those and leave a 3 in the denominator. Those will cancel with those and leave an x in the numerator, and so I get something like the absolute value of x divided by 3. And again, what the ratio test says, if that is less than 1, then my function converges. And of course, if that's greater than 1, it will diverge. Okay. One more step, right? Because absolute value of x divided by 3 less than 1, I could rewrite this part as absolute value of x. I can multiply both sides by 3 is less than 3. Oops. Which is telling me, again, over here, what's the domain of this function? Well, I know if the absolute value of x is less than 3, then it will converge. That's part of the domain of the function, right? So I know as long as x is between 3 and -3, right, that is part of the domain of the function. And the only thing I don't know is what's happening at those endpoints. I don't know what's happening when x is equal to -3 or when x So notice, centered around 0 here, I can go 3 units to the right or 3 units to the left, right? And so here, that number 3, if I have it written in this form, is called my radius of convergence. So we'll see what that really means is, everything's sort of centered around 0, and I can go 3 units to the right, and I can go 3 units to the left, and I know I have convergence, or the domain are all those points. And I understand over here and over here, those are all points that are not part of the domain of the function, because that sum is going to be divergent, right? The rule's not going to make sense. And then the only other thing to decide is what happens at 3 and -3, if it makes sense to do so. Okay. All right, so again, I'm most interested at the moment in just trying to figure out what this radius, again, what are most of the points that the ratio test tells us for which we have convergence, and what are the points for which we don't have convergence. Okay. All right, so we have that. Yeah. Okay. And then if I want to know what's happening at the endpoints again, I could plug those endpoints in. Now, it won't be a surprise, right, that what I have up here is a geometric series, right? This is a geometric series. It's like x over 3 to the nth power, right? And I already knew that in terms of a geometric series. That's why when I take this limit, there actually are no n's left, because I actually started with the geometric series, both of the last two cases. Okay. And just like before, because it is a geometric series, I know that this thing will sum to 1 over 1 minus x divided by 3. Right? 1 over 1 minus r, right? 1 over 1 minus x divided by 3. I mean, if I wanted to, I guess I could write it as 3 over 3 minus x, if I wanted to. Write it as 3 over 3 minus x. Okay. And that will be true as long as the rule makes sense, right? And the rule will make sense as long as x is between -3 and 3, and a little bit more to worry about maybe in a week of figuring out what's happening at the endpoints. Okay. All right, so let's do one where there's not, it's not exactly a geometric series. All right. I don't know, we could do this one. F of x equals sum n equals 1 to infinity, and let's say n times x to the n. Okay, there's a good function. Right, again, I want these power functions, I want these x to the n's here, and then it's just, I might have something else out in front here. Right, again, ratio test. Right, the question is domain. What's the domain of this function, right? Ratio test would tell me, let's look at a sub n plus 1 over a sub n, absolute value a sub n plus 1 over a sub n. Be like the absolute value of n plus 1 x to the n plus 1 divided by n x to the n. And then I go ahead and simplify things, x to the n plus 1 over x to the n. That's just like having an x in the numerator. And then I have this n plus 1 over n. So maybe I'll write it as absolute value of x, and then absolute value of n plus 1 over n. Okay, if I can ever get that x out by itself, that's great. That's kind of what I want to do. Okay, because I now know, as n goes to infinity, n over n plus 1 is like an n over n, which is like a 1, right? So this thing here converges to 1, and this whole thing will converge to the absolute value of x times 1 as n goes to infinity, right? So it will converge to the absolute value of x. Okay. And now I know this function, as a function, will converge as long as that is less than 1. Okay. So again, I have this, what I call a radius of convergence of 1, right? Because I write it this way and I can see, as long as, in terms of the domain question, as long as the absolute value of x is less than 1, it will converge. When the absolute value of x is greater than 1, it will diverge. Okay, and that would mean between -1 and 1, right? Those would all be parts of the domain of the function. And the only thing else I have to look at is what's happening at 1 and what's happening at -1, right? So what's happening at the endpoints, should I include them or should I exclude them in terms of convergence? Okay. So I know absolutely between -1 and 1, like before, it converges. I know absolutely, right, they will diverge outside of the -1 and 1. And then I'm still leaving as a question mark what's going to happen at 1 and -1. And you can look through and you can plug values in. You can see, oh, those will diverge also. Okay, they will both diverge. All right. Let me see. Okay. Well, I'm trying to decide here. We could potentially do one more. Sure, why not? Let's just do one more. And let me make it a little bit more complicated. So notice, right, it really, this n, it's an algebraic term. And notice, if that wasn't there at all, my radius of convergence would still have been 1. And the fact that I have an n there to make these things larger didn't change that. Okay. At most, it could only change what's going to happen at the endpoints, at that 1 and -1. Okay. So I can kind of see, depending on what types of terms I have in there, what that radius of convergence might look like. Okay. So let me show you something that I would say has an infinite radius of convergence, right? So this one is going to be a function that I can plug any number I want to in it, right? Anything from -infinity to infinity. And so here's what it will look like. Let's see, let's get rid of all this. One last example. And of course, if I want to do this, I need something that's going to grow faster than x to the n, and an n factorial will be that thing. So here's what I'm going to look at. Sum n equals 0 to infinity, x to the n over n factorial. Okay, as I mentioned a number of times, this sort of power here, getting increasing powers, is going to grow quite large, quite quickly for large values of x. But factorials grow faster. Okay. They get bigger than what we have up here. Okay. So here's a function, right? And I want to know what the domain of this function is. And the way I'll answer the domain of this function is I'll look at those a sub n's, right? Those x to the n over n factorials. And I'll look at a sub n plus 1 over a sub n, right? I'll look at the ratio of those consecutive terms, right? Because what I'm doing is comparing it to a geometric series. And I say, okay, well, I understand that I have that, which I could simplify as x to the n plus 1 over n plus 1 factorial. And then the denominator, I'd be dividing by this, but I'll take the invert, I'll invert and multiply, take the reciprocal, n factorial over x to the n. We actually did this one not so long ago with a 2, did it in class, did it with a 2 here instead of an x. Now we're just going to do it with an x. Because what's going to happen here is that is going to cancel with that and leave an x in the numerator. And as we've seen before with factorials, the n plus 1 factorial and the n factorial are going to cancel and leave an n plus 1 in the denominator. Okay. So what I have is an absolute value of x over n plus 1. Okay. Whatever x is, regardless of how big it is, how small it is, whatever number it is a number and it is a fixed number, right? Remember, the question is, what numbers can I plug into this function? So I'm going to plug a number into this function so that this rule makes sense. And so it's going to be a number, okay? But now, whatever number it's going to be, I'm going to let x go, or n go up to infinity, right? Because I really want to know what's happening for large values of n. And note, what's going to happen is x is going to stay x, whether it's a 1, or a -1, or a 15, or 1,000, or a 10 to the 23rd power, which is a pretty big number, right? Whatever number it is, sooner or later, as n goes to infinity, that is the thing that's going to dominate the whole thing. That's the thing that's going to be large. And so we'll get something like an x over infinity, which will be for limit 0. Okay. Right. We'll get a 0, right? So it's like getting an absolute value of x times the absolute value of 1 over n plus 1. And of course, this thing, as n goes to infinity, that's getting closer and closer to 0. Okay. And again, the question is, what values can I plug in for x and make sure that that's less than 1? Well, 0 is always less than 1. Okay. So it doesn't matter which x I try to do, the limit will be 0, which is less than 1. And so my domain here will be all real numbers. All x. I can plug in any x I want to, ranging from negative infinity to infinity, and this thing is going to converge. This is a situation when that happens, right? When I actually take this limit, the x completely disappears, so I get 0, right? I get 0. 0 is always less than 1. This is the case where I'd say my radius of convergence is infinity, or I have an infinite radius of convergence. So here's a function that will converge no matter what number I plug into it, right? Which is nice, right? So even though I'm taking really large powers, like 1,000,000 to the 1,000,000th power, right? I'm dividing by 1,000,000 factorial, okay? And then later on, I'm going to take the 1,000,000 to the 1,000,000th power divided by 1,000,000,000 factorial, and then trillionth, and so on and so forth, that this thing will get large faster than that thing. Even though the sum will be potentially large, that's what I'm going to get, okay? So here's a function that would be defined for all numbers, right? All real numbers, no exceptions, okay? No boundaries, no endpoints. Anything that I want to plug into it. Okay. And then, right, again, part of what we want to do with power series, and I'll leave it here, part of what we want to do with power series is to not just look at these series as they are, but we want to understand better what functions they represent. And this is a function that we've seen in terms of Taylor polynomials, that if I cut this off at a certain point, I ended up with a Taylor polynomial. But if I let it go off to infinity here, I will not get an approximation of e to the x, but it's exactly equal to e to the x. Okay. So that this is another way to represent that function right there. And it's nice to have multiple ways to represent functions, because sometimes we want to do different things with them. And again, you don't need to know this now, but that's what we would have. So when I made a claim on Monday that, in this case, sum of x to the, 2 to the n over n factorial, I think this was the first example we did with a ratio test. When I did that, I saw that, I claimed that that's going to sum to e squared. How do I know that? Because in the not too distant future, probably next Wednesday, maybe Thursday, maybe next Friday, a week from now, we will show that, in fact, this function, which I can define this way, I can also define in that way, show that they're the same value. They're the same value for all possible x values. And it just gives me another way to think about that. So if it's true for all x values, it's definitely true when x is equal. Okay, there you go. So that is power, the ratio test. That's the big one. Okay. I'll put this in an email that I send out related to these things. But in this section, which is, here we've been talking about 10.5 and 10.6. And in 10.5, there's another test called the root test. Root test is not important. Don't worry about the root test. Okay. It does not come up enough that we should essentially worry our brain cells with it. So we're not going to worry about that. So the ratio test out of 10.5 is sort of the important one, because it's the one that's going to allow me to find the domain of this function for most values. It's going to be able to tell me what works, what doesn't work, except for possible endpoints. Okay. There you go. All right. So we'll stop there. This takes us into fall break. Give you a handful of homework questions, probably from a little bit more with 10.5 and a little bit with 10.6, so that we can start looking at these power series and looking at the domain of these functions. And we won't be worried about the endpoints yet. We'll bring that back in a little bit. Okay, have a good break, and I'll see you guys on Monday.